Good morning. Today I'm going to present to you on refining fault current limiter by using finite element analysis. But before that, I want to introduce myself. My name is Clinton Crony and my supervisor is Dr. Jeff Mosgrove, and we have working together for 6 months. So I want to explain to you my general layout of my presentation. So there are 4 main components in my presentation. The first one is I'm going to explain to you briefly what is fault current limiter, what is today's power network trend, and what is its definition. The second component will be why do I choose saturated core fault current limiter. I'm going to explain to you what its advantages, its basic operation, and it also has some disadvantages. The third component will be how do I carry out my experiment or thesis. Basically, I did a lot of background reading, simulation using finite element analysis software, and also analyze it. And the last one will be future works. So we should start the first one. So what is fault current limiter? Before that, I'm going to explain to you in today's power network trend. So today, we know that there's a lot of houses, a lot of companies that need power. This means that the increasing needs of this power network means increasing fault current or short current. Some other researchers propose some solutions such as total rebuilding of the whole thing, but it is not a really practical approach because it's just too hard to do it. Then a call for a suitable solution is needed, hence fault current limiter. And the basic definition of fault current limiter is that it's a device that used to limit the current when a fault occurs. So ideally, fault current limiter during a non-fault event, it will impose negligible impedance. On the other hand, during the fault event, it has high impedance, thus limiting the current, the fault current. There are also some few other technologies of fault current limiters such as solid state FCL, superconducting resistive FCL, and the one that we interested in, saturated core FCL. So why saturated core FCL? I'm going to tell you about its advantages, its basic operation, and disadvantages. So we go to its advantages first. So one publication say it is a fast and effective current limitation, and also immediate fault recovery and fail-safe operation. Means that whenever there is a fault happening in the system, it will still standing as a unit. So it's basic operation. If you can see the screen here, you can see the figure there. There are 2 coils on the outer limb and the DC coil is placed on the middle limb. So the DC coil acts as a superconducting coil that used to saturate the iron core, and the AC coil is the 2 AC coils carry the AC load current. Okay, in terms of its magnetization characteristic, during non-fault event, the current from the AC coil is too small, thus it cannot desaturate the core. This means that at this time of point as well, the fault current limiter is imposing negligible impedance. During a fault event, the fault current is high enough to desaturate the cores. Thus, it will make the terminal impedance is fully maximized. But how fault current limiter imposes negligible impedance? So, by looking at this BH curve and understand it, so the first, DC coil that we just saw just now saturate the iron core, and then the current that was induced, it will bring the iron core into saturation. Now, saturation will occur once it reaches the knee point, which is, you can see there, the magnetic saturation. At when it is saturated, the permeability of the core is equal to 1, which is equal to air. At this point, when the permeability of the core is 1, the AC coil sees the core as air. So that's the reason why the impedance is negligible. So there are also two big problems that the researcher need to deal with. The first one is size and weight of the SCFCL. If you can see, if you still remember the figure just now, there's a lot of iron core and big impedance of DC coil. And the second one as well, the coupling effect between AC and DC coil, is that both AC and DC coil, they are sharing the same magnetic path, so that's why there's a coupling effect between them. So the problem that I want to solve is that how do I want to reduce the size or weight of the SCFCL? That is my main objective of my thesis. Is there any possible way that I can use to refining the saturation core? Okay, this is the methodology that I carry out. The first one I did is background reading and simulation and analysis and discussion of my analysis. Doing some background reading made me understand the background of how it works, how fault current limiter works, and also I can find a lot of various design of FCL. And then I came up with two designs from two different publications. So the first one is, if you can see here, and the second one. So the first one, they have 2 limbs. The second one, they have 3 limbs. So as you can see at the top there, that's the software that I use, and these 2 models are the one that I built in the software. So if you can see here, the black color represent the DC coil and the green color represent the AC coil. Note that I use a simple set of parameters to simulate my model. So the result is, I'm going to compare between the current waveform and flux density versus time, and I'm going to compare my result and with the ideal one that I found in the publication. So the first one, current waveform, as you can see there, ideally the current, if you can see the current there, the high current is the one that we want to limit, which we call the prospective current, and there's a small current there, we call it limited current. But if you can see in my graph, it's kind of limiting the current, but it's not to an extent it's very clear to see. I'm going to tell you the reason in a minute. The second graph is flux density versus time. This we observe the AC magnetization. So if you can see in my result as well, it doesn't look like it. There's some reason of it. So the possible reason might be, for the current analysis, big possibility that I use an incorrect set of parameters. Remember when I told you that I use a simple set of parameters such as 1 volt, 1 ampere, 0.01 millihenry. So it's a simple set of parameters. It doesn't according to the rating. For the second one, for the flux density versus time, big possibility that I use incorrect dimension. As for example, if the core is big, it's very big, but the coil is doesn't have enough impedance, it will not saturate the iron core quite good. So there might be some error in that simulation. So the last one, future works. So by looking at my result there, I'm going to do in future works, if I'm going to do active 458, I'm going to do in-depth simulation, so more simulation will be taking place. And second one, further extensive analysis on finding the suitable dimension of the coil, or and the core as well, so it can saturate the core efficiently and finding the correct impedance for the DC coil and also the DC voltage. That is all. Thank you for listening.